And I would like to thank all of you for being here, for sustaining me for the past 5 days or past week. So today, what we're going to do today, as I was promising all the week, we'll be focusing today on direct numerical simulations. Okay. So the first thing I would like to talk to you about is we'll talk about evaporation. You already had some sort of a hands-on session on Monday where you just deposited a droplet. Okay. Now, when you want to let the droplet evaporate, I'm going to tell you the physics behind it. I'm going to show you the equations behind it. I'm also going to show you several treatments that you can do, okay, if you want to change your system. Okay, but once we do evaporation, we'll go on to boiling because that's another challenge as well. Okay, so very quickly, what do you mean by direct numerical simulations? What is your understanding of direct numerical simulations? What's the difference between direct numerical simulations and CFD? Do you have any view on direct numerical simulations and CFD? Sorry?
In DNS we solve the entire problem, but in the lines-based we solve by taking the average of property.
Okay. So yeah, I mean DNS is basically solving the pure governing equations. No assumptions being made everywhere. Okay. So you're not assuming that heat transfer is not there. You're not assuming, you're solving everything as it is. Okay. In case of turbulence modeling, we have some approximations. Okay. So that's where you have Reynolds average, Navier-Stokes equations and all that. Okay. So that becomes, so when you use RANs or when you use LES, it's not DNS anymore. It's an approximation. So the most accurate answers you get for fluid mechanics computationally is through DNS. Okay. CFD is a general term. Okay. DNS is proper CFD. DNS is basically you're putting the physics as you see in reality. Okay. You're not making any assumptions there. You're not saying that, okay, I'm not going to take the turbulence parameter. I'm going to have this model there. Okay. So there's no contamination in a DNS. So basically, obviously, as you already know, if you want to study fluid mechanics, you have to rely on experiments. You need to rely on proper experiments, proper instrumentation, and the first thing before you set off for any problem, you need to ask yourself, what do you want out of it? Okay, what do you want to get out of it? What is the ultimate objective? Okay. Then, of course, there is another arm to this. You can use theory. So we have seen a lot of theoretical modeling before in the past week. You can do stability analysis. You can do lubrication. There are other things as well that you can do. Okay. So theory is there. But then you also have DNS. So these are numerical simulations. These are numerical solutions of the fluid mechanics equations. Now, obviously, as you already know, there's a Nobel Prize. So if you're able to get a solution of governing equations of flow, you will be out for a Nobel Prize or a Nobel Prize. Okay. So basically, if you have a non-numerical solution, it's going to be very tough. But people have claimed that they are able to do some things about it. Okay. So basically, these are the three arms of fluid mechanics, and all of these things together form machine learning. Well, you get data from machine learning and all that. So machine learning is not anything different. We've been doing it for ages, but now it has a new name. Okay. So DNS are basically numerical solutions of flow only using the Navier-Stokes equations or governing equations in general, without the use of any models. Okay. Without the use of any approximations, without the use of any model. Okay. One of the key models are basically turbulence models. So can someone tell me why is turbulence so hard to simulate?
Because we have to, in the case of turbulence, we have to capture the Kolmogorov length scale. That is the smallest length scale to get the approximate.
Perfect. So basically, it's the smallest eddy length scale. That is the Kolmogorov scale, or usually represented as eta. Okay. So in order to take that into account, you need to have extremely fine grid, and typically when you have an extremely fine grid, it's a very large simulation. Okay. So that's why one way to resolve that is by having some sort of a approximate turbulence models. Okay, are you aware of so within RANS, many people mention about RANS. What is the main problem with RANS modeling? Say, what is the most common RANS model that people use? K epsilon, yeah. If you go to industry, the first thing they do is apne K epsilon kiya gaya, or K omega, or whatever. It's the favorite model. K is basically the strength of the turbulence energy, and epsilon is the dissipation rate. Okay, dk by dt. But the thing is, the problem with that K epsilon model is basically you're actually, when you have a turbulence model, if you use the RANS equations, there is a term ui dash uj dash whole bar. So this is basically, this is the main term, which is the Reynolds stress term, and there is a mu, there is a rho or a mu rho in front of it. So this is the Reynolds stress term, and this is always a question mark. So turbulence models always have some sort of an approximation to solve this model. Okay, and if you look at this uij uj dash, it's not a vector, it's a tensor. So basically ui dash uj dash is in 3 dimensions. It will be u dash squared, u dash v dash, u dash w dash. Again, this is the v direction, so v dash u dash, v dash squared, v dash w dash. Again, you will get w dash u dash, w dash v dash, w dash squared. So this is pretty complex. So for each and every term in this tensor, you need to have a model. Okay, so there is actually a story. So there is something called as Reynolds stress model as well within the RANS system of equation. And some of these older RSM models, they used to have about 9 or 12 constants, empirical constants, C1 to C12 or something like that. And the joke is that you can fit an elephant in it. It depends upon, no one knows what number to use there. Okay, so basically that is the problem with these turbulence models, is that they're very empirical. Okay, and there is no such, I mean, nowadays we know, nowadays we probably have some idea about how best to use them, but again, it's a lot of trial and error. Okay, people use turbulence models, people use K epsilon models for boiling, condensation, but and we do compare it with experiment. If it falls within 30% of the error, we feel very happy about it. Okay, so they're not the best models, but they're there. Okay, but when you do DNS, the biggest advantage you have is it's accurate. Okay, as long as your errors are controlled, you're accurate. Okay, as long as your mesh is good, you're accurate. It has all the details. The problem is it is extremely expensive. It's computationally expensive, and that's why you need to have some sort of a supercomputing cluster to do this. Okay, so nowadays supercomputing clusters, I think given that we have clusters everywhere, it's probably easiest to do DNS at the moment than give an incorrect answer using a turbulence model. Okay, obviously when you have these clusters, the most important thing is you will probably get a result. You probably get a result of a very difficult simulation within a day. Within 24 hours, you can parallelize your simulation and you probably will get an answer. Then the most important time, the most of the time is taken into post-processing the result. Okay, earlier you used to take about 40 days to run a simulation, and probably another 40 days to post-process your result. Nowadays, you probably have 12 hours to run the simulation. You can easily get an answer, but then you use 40 days to really analyze it, because the amount of data that you have is huge. Because typically, if you solve your Navier-Stokes equation, definitely you will get the velocity field. So you will get the velocity field. So UVW. You will get pressure. If you have heat transfer, you will get temperature. If you have mass transfer, you will get concentration. Okay, so obviously, and this is concentration in space as well as in time. Okay, P in X and T, T in X and T, concentration in X and T. So this is a huge amount of data. There's a huge amount of data. that you request. Okay, and on top of it, you also have geographical data. You have the domain coordinates. You also have the time stepping coordinates. So you can imagine the amount of data that you can generate using a DNS. It's probably even for a single time step, it can go to easily up to a gig. Okay, so you need to be careful in first of all determining what you want out of the data, what you think is most useful for you. Okay, so obviously one of the things that you can see is if you have more number of operations, if you increase the number of equations that you're solving, it will scale as Reynolds number cubed. So it becomes a very expensive simulation. But nowadays with supercomputing, it's not computational. It is expensive, but at the same time, most of the time is spent in post-processing the result. Okay, so within my group, we develop a number of flow solvers. So one of the flow solvers you did have an experience on. It was called as TPLS. It is a very old name actually. I want to change the name, but given that I've been named Padagaya, so I didn't really bother to change it. It was called as two-phase level set solver, but we know that level set methods have got severe constraints. So we have another alternate method called as the diffuse interface method. In a diffuse interface method, the interface is diffuse, but it gives you a lot of opportunity to ensure you can do phase change, you can do contact line dynamics, you can do interfacial reactions, you can also do simple non-phase change flows, stratified flows, etc. You can do everything. So this is a much more powerful method in comparison to level set, and may I say also volume of fluid, because you need to make assumptions in those methods which you don't need to make in the diffuse interface method. Okay. The other methods that we develop is immerse boundary methods. So we have done a number of these things. So the immerse boundary methods are basically, the first method was done using Jeris. Okay, we incorporated an immerse solid solver. We also have a I'll probably put a link there so that you guys can download if you want it. The main problem with this particular method is that it was not greatly parallelizable. Okay, so we did for single solids, immersed solids, how they tumble, etc., etc. We did that, but we were not really happy with the parallelization. So we have embarked on a new thing called as XCompact 3D. This is a very powerful immersed solid solver, and it can take into account number of solids submerged in flows, and we're using it to determine clouds, hydrate slurries, and so on and so forth. And the most important thing that you want from a DNS solver is not that you're solving the full equations. It's that you're solving the equations in 3D. Okay, they are highly parallelized. Okay, so that you can maximize the efficiency of your computational network. Okay, and basically for each cluster that you use, you have to optimize this. Okay, so normally, so that's why I'm not a computational scientist. Okay, I'm not a computational scientist. I know the physics of flows somewhat. Okay, I can develop the equations, I can give them, but what I do is I work very closely with computational scientists to make sure that my code is as efficiently parallelized for that architecture as possible. I'm not the one who's an expert in parallelization. I admit that. The first time I did it, it was a mess. Okay, they know it best, so let them do it, and I'll do the physics, I'll do the analysis, I'll do the rest. Okay, so that has been my approach. So we have in Edinburgh, we have something called as the Edinburgh Parallel Computing Center, who have specialist people who are completely into. They have physics background, they have physics and engineering backgrounds, but they're mainly into parallelization. Okay, they look into GPU architectures, they look into Cray architectures, they can look into Intel architecture, and they'll tell you, okay, this is your code, this is not the way to do it. For this architecture, this is a better way. They will also advise you some of your internal methods. So for example, we had a pressure solver, which was not great. They completely changed it to conjugate gradient method. They also are aware of better numerical methods to make sure that you can maximize the speed. Okay, so initially there is a lot of effort put into optimizing your code, but it reaps rewards later on, because at least you don't need to do it later on. Okay, and you can access as many cores as possible. Okay, so so in my group, we do a lot of these things. So all my PhD students, they have something to do with theory, either stability or lubrication. Debrishi is doing a lot of lubrication. But then they also do some experiments with my collaborators so that we understand that our theory is not nonsense. And then we also do some simulations. Okay, they also develop flow solvers. Okay, so one of the examples I would like to talk to you about is evaporating droplets. Okay, in this example, this is the first example we did back in 2013 and 14 and 15. Okay, so this is a very old one. Now, one of the questions, if you look at the literature at that time, everything was like 2D symmetrical domain. They took a droplet, they cut it into half, they just solve it and tell you the answers. We asked the question why? Because in reality, you would never get a spherical droplet in nature. You always have something like this. Okay, you always have something like this. And even if you have a spherical droplet, this is our so-called hemispherical droplet. This is a methanol droplet on a hot plate. You can see these patterns which are not at all symmetric in any way. So when people assumed a symmetry boundary condition, they cut off the azimuthal currents. That means the heat transfer, that is the convection currents in the azimuthal direction are cut off, which means that the heat transfer they predicted is completely incorrect. Okay, completely incorrect. So, and also what we found is through DNS, we could see that the vapor currents are also pretty strong, which is again ignored when you do a symmetric boundary condition. So that's why we said, first of all, the shapes of droplets are usually never spherical. So they have a weird shape like this. They have weird contact angles. They have sharp corners. They've got corners with larger curvatures. They have corners with little curvatures, and so on and so forth. So you get a lot of complexity there. Okay. So what we did was we started off with the simpler problem. The simpler problem is hemispherical droplet. Why? Because everyone else, my ancestors did that. So I wanted to do it. Okay. Everyone else did it, so let's do it. So what we did was basically we take a liquid, it's placed on a hot plate, and basically it's in a domain which is completely gas. So this is a liquid phase, that is the gas phase there, and basically it's doing its job. It has to evaporate. There was a lot of discussion on boundary conditions on the sides. I'm going to come to that in a moment. Okay. But before we do that, the most important thing is all my solvers are non-dimensional. Okay. So I decide on what are my length scales, what are my velocity scales, and so on. So in this case, I scaled the length with respect to the height of the droplet, the velocity as the capillary velocity, okay, capillary velocity. The pressure is the capillary pressure because it's such a small droplet. I have not assumed it is smaller than the capillary length, larger than the capillary length, and so on and so forth, okay. I've not assumed any of that. You've got surface tension. You've got surface tension as a function of temperature. You also have this is the temperature. So basically, if you go through the entire thing, you will get some kind of a Reynolds number. You will get a Jacob number, which is the ratio between sensible heat and the latent heat. Obviously, in the gas phase, you've got diffusion, which is occurring. Because it's a pure liquid, we assume that diffusion within the liquid phase you don't need to consider. It's basically diffusion within the gas phase. This way the Schmidt number comes into picture. You've got the Weber number, which controls the shape of the droplet. You've got the interfacial Peclet number. I'm going to come to that in a minute. And you've got all these density ratios, viscosity ratios, conductivity ratios, you name it. You get everything. Okay. So this is how this is what you get if you have a single droplet. So what we're going to do is we're going to look at these equations a bit carefully. Now, if you look at this, typically, I don't know how many of you are aware of volume of fluid method. Level set, are you aware of level set? So mostly volume of fluid and levels. So typically, in any sort of a method, when you have a liquid and a gas phase, you have an interface. This interface will move. And one of the standard equations, what people use to move this interface, is advection diffusion equation for the interface. So which is something like del phi by del t, phi being the interface, okay, plus some velocity dot grad phi equal to 0, something like that. Okay, this is there for level set. In case of when it is level set, phi is the distance function with the interface. In case of a volume of fluid, you got a constant, you got the volume fraction, and so on and so forth. Okay. What we are using is, so this in the volume of fluid method, you get something like this: u dot grad c equal to 0. Okay. What we are doing is we are going away from the volume of fluid method. Okay. And there is no method which is called as a sharp interface method. Whether you're using a level set method, whether you're using a volume of fluid method, this is always a part of a grid. Okay, there's always a part of a grid. There is always a small gradient of phi or c. So the interface has certain thickness, always. Okay, you can minimize it as much as possible. People can say that it's approximated to a sharp interface, but it will have some interface. Okay, so what we're going to do here is we're going to look at a different method called as the diffuse interface method. Now, in a diffuse interface method, what happens is you've got a fake diffusion term. So you have del C by del T plus U dot. It's very similar to what your volume of fluid method is, but it has a diffusion term, something like del C by del T plus U dot grad C equal to some diffusion coefficient grad square C, and this is basically called as interfacial diffusion coefficient. Okay, and this interfacial diffusion coefficient is not a mathematical thing, it's basically a physical thing. It is obtained from van der Waals equation. Okay, and this is the interfacial Peclet number derived by the interfacial diffusion. Okay, this m is the mobility term based on the mole fractions, based on the materials that you're using. Okay, so basically, and here this small phi, so C is the volume fraction between gas and liquid. Phi is called as the chemical potential. There is a major advantage of this method. The advantage of this method is that you can solve contact line problems without slip velocities. The other advantage of this method is because it's a diffuse method, because it is a diffused method, okay, it has a certain, the interface will always have a certain thickness. Typically it is 1.5 delta x being the size of the grid. Okay, if you have a thick interface, then whenever you have mass transfer, you can easily fit in a kind of a mass transfer profile here. Okay, if it was a sharp interface method, you have a concentration jump. Okay, and whenever you have a concentration jump, numerically you will always get a singularity. So at least that is avoided. You can make it as smooth or as sharp as possible. It has a major advantage. But the critical advantage you have is this is very good for contact lines. Okay, there is also a disadvantage. I'm going to come to that disadvantage very quickly. Okay, so this one is the Cahn-Hilliard equation. Usually this is equal to 0. Okay, in this case it is equal to S. S is the phase change. Okay, so whatever evaporation, so basically the mass loss, so if there is a loss of mass from the liquid phase to the vapor phase, the interface will drop. If there's condensation, the interface will grow. Okay, so there is no restriction. The same method can be used for condensation as well. This is the usual continuity equation. Typically grad dot u equal to 0. This is your continuity equation. But here there is mass loss. So basically there is a phase change parameter. So if there's a mass, if there's evaporation, you lose the mass, and that mass is fed to the gas phase. So that's what this does. Okay, so there is always a mass balance. The other thing is the energy equation. So the energy equation is very similar. You've got the transport of temperature here. You've got the thermal conductivity, and if you have phase change, you will have the energy of phase change, which is dictated by the ratio of the ratio of the sensible heat to the latent heat, depending upon the latent heat. Okay, so basically you're accounting for the latent heat as well. Okay, the other thing is obviously the usual momentum equation. If you look at the momentum equation, it is very similar to what you have here, what you have everywhere. This is basically your surface tension term. This is surface tension as your temperature changes. So this is where your Marangoni number comes into picture. This is basically how your surface tension changes across the interface. Okay. Usually you will also have a rho g term. Okay, and typically this rho is represented as some bond number there. In this case, for these experiments, we calculated the bond number and it was very small, so we ignored it. But even if you have a bond number there, it doesn't make a difference. Okay, so basically you will have a bond number, and the bond number, it's very important to understand the bond number. The bond number, it talks about the strength of surface tension to gravity. Okay, the strength of surface tension to gravity. The other thing it also looks into is basically buoyancy effects. So if you have a lot of density change, then I would have considered bond number. Okay, but in this case, it's not of a great value. Okay, we also account for, if you heat a liquid, the volume expands. So we also account for that, but we found that in this case it's very, very small. So we just ignored that. So obviously, so this is what is happening in the momentum equation for the liquid as well as the gas phases. Now, the gas phase specifically, all your evaporation that happens, it starts populating the gas phase. So you've got species equation in the gas phase. Okay, you've got species equation in the gas phase. The more you evaporate, the more species you have. So therefore, there is an S term here. S is the phase change model. And what is the phase change model? Phase change model is based on Raoult's law. This is a practical Raoult's law. This is the practical way in which liquids evaporate. Okay, so Raoult's law typically is represented as it's a vapor-liquid equilibrium model. Okay, for those who have done vapor-liquid thermodynamics, you will know it's a vapor-liquid equilibrium model. It relates the mole fraction in the liquid phase to the mole fraction in the vapor phase. So it is simply YIP is XI PI saturated. This is the vapor pressure. So, and vapor pressure is always a function of temperature. So you can see that because you've got temperature, you will have a temperature variation across the interface. So at each point you will have a different vapor pressure. Okay, and that will dictate your evaporation. Okay, so this is basically how it is done. PS is basically I think saturation pressure, and this curved P is basically ratios. M is the ratio of the mole fractions, and so on and so forth. Okay, so this is how your phase change model is. I'm going to come to the drawbacks. The first assumption I have made here is that I'm using a vapor-liquid equilibrium model. In an evaporation system, when you consider vapor-liquid equilibrium, it means this is slow evaporation. It's a very slow evaporation. At each state, we assume that there is equilibrium between vapor and liquid. Okay, this is a very slow evaporation. The other assumption is of the Cahn-Hilliard equation. So whenever I implement the Cahn-Hilliard equation, the Cahn-Hilliard equation obeys the boundary conditions very strictly. Okay, if you impose a no-slip boundary condition, the interface will not move. It's a pinned contact line. Okay, so your droplet is there. As it evaporates, it will change its contact angle. Okay, if I want to have a dynamic contact line, I need to indicate the contact angle. Okay, so if this is the contact line boundary condition which you can impose. Okay, if you impose this contact line boundary condition, that is applicable only at the interface. Okay, what it tells you is, depending upon the size of the contact angle, it will give you a Cox-Voyanov velocity. Okay, so if you don't give any contact angle, if you have a completely no slip boundary condition, then your contact line is fixed. It just depletes itself in that way. If you give a contact angle, it's going to move with that constant contact angle. Okay, so if you supply a contact angle, you actually have dynamic contact line. Okay, you can have an advancing angle, you can have a receding angle, and it will take into account hysteresis, and it will do everything. Okay, so that is so with Cahn-Hilliard method, you cannot switch from being a pinned contact line to a dynamic contact line. You can either do one at a time. We have actually done hybrid, but it's basically just for animations and fun. But physically, it's not correct. Okay, so this is the method that we use. So here you can see everything is with respect to, it's a transient model. You've got a three-dimensional space parameter here, and so everything is done in 3D as well. Important thing about is boundary conditions. So in the boundary conditions, obviously your temperature is constant. This is a hot wall, so we don't use a heat flux condition. We use a temperature condition here. The next important question we ask is, what should be the boundary conditions at the top? How high your box should be, and how low your what could be the boundary conditions? If you have a very small domain, and if you set your top boundary condition to be a Dirichlet condition, something like not T equal, this is a Neumann condition here, but if you set it as a Dirichlet condition, that concentration is 0, you'll have excessive evaporation, because your solver will try to make sure that your concentration at the top of the droplet is something, and it will immediately suck off. So there's a lot of artificial sucking going on. If you want to make sure that you're able to make experiments, you need to have a sufficient height of the domain. We found that the typical height of the domain is 20 times the radius. Okay, so this is approximately 20 times the radius. Okay, to have more plausible results. Okay, to have better results. The sides of the domain is the same is true. If you have a very narrow domain, you'll have evaporation, accentuated evaporation from the sides. You don't want to have that, because in your experiment, it's a free domain, evaporation is consistent in all directions. So you need to make sure that you have, so it's 20 R in this direction, 10 R, or probably 20 R in this direction, 20 R in that direction. Okay, so that helps you make sure that you're able to manage your evaporation properly. Okay, and typically, what are your initial conditions? The initial conditions is only that you have a temperature there at the wall. Everywhere else, the velocity is 0. You have an initial cap. That's it. You have an initial cap, and probably the concentration field in the vapor phase is 0. So omega equal to 0 in the vapor field throughout. Okay, so that is basically, and we also put, actually, given that there is a temperature here, we put a kind of a thermal gradient across, so that I don't have to calculate it. So it just is there. Okay, so this is what you have. So I was talking about these things earlier. So typically, this is a further explanation. This parameter in the Kahn-Hilliard equation is the mobility parameter. I'll tell you, Kahn-Hilliard equation has been used extensively for miscible mixture. If you talk to physicists, when they model LCDs in your screen, LCD displays and all that, they use the Kahn-Hilliard equation. So it's an excellent thing, especially when you have miscible mixtures. Here we're using immiscible systems. So you need to have the surface tension parameter. Okay, so we are aware of how good the equation is. You've got these parameters. I mentioned about m, which is the mobility parameter. Phi is the chemical potential. And if you do a free energy balance, you actually back out your van der Waals equations for free energy, and you get surface tension. So you can back out surface tension. So there is no problem. Okay. And as I mentioned, you can have a contact line boundary condition which is looking like this. If you supply a contact line contact angle theta a or theta r, based on that, it will give you a contact line velocity. Okay. So this is a check. This is basically a 2D snapshot of a 3D domain. This is a very simple case. We just want to check if your temperature profiles are correct, if your mass fraction profiles are correct, and if your velocity profiles are correct. We are okay with it. This is very similar to what is expected. Okay. But again, what we are here for is looking for 3D systems. So the first thing we did is we looked at experiments. Okay. So we have this experiment. This is a water droplet on a copper plate, very simple one, nothing fancy, simple experiment here. And what you're seeing is you're observing through an IR camera. Because it is water droplet, you will not see any activity on the interface much. But what you will actually see is you can capture how your evaporation happens. So this is at various times. So this is initial time. This is the thickness of the droplet. Obviously, you can see that the droplet is almost pinned for a large portion of time. So almost for 80% of the time, it is pinned. So we wanted to just check if we are able to replicate this. Okay, so this is from experimental result, and this is your IR image from the top. Okay, and you can clearly see when you have a larger droplet. I think it was 60 degrees. I don't remember what the contact angle was. Anyway, when you look at the larger droplet, you can see that there is a cold point here, and you've got maximum temperature at the sides because it's at the contact line, which is expected. Okay, so what we have done here, if you see the blue and the black lines are simulations, and the blue lines are experiments. So the first thing is this is the change in contact angle with respect to time. You can see that okay. If you see the black line, it is almost going like the blue line, but at some point it starts deviating, and we know the reason why it deviates. If you look at the radius, if you look at the height, if you look at the height, it has a very similar feature. You can see some deviations occurring at this point. If you look at the radius itself, after some point you can see the deviations going on, and this is how your volume of the droplet changes with time, and you can see deviations there. The reason we have deviations is in an experiment, we had no control on what the droplet does. We saw that it is pinned from the eye, but actually it's slowly moving. And in fact, I'm going to show you the final state of the droplet. The final state of the droplet looks very different. This is again, we were looking at even dynamic contact lines, and we did the validation. That's not there. I should have shown you. Okay, anyway, I'll come to that. So if you look at, so at least we could compare when the contact line is pinned, we could compare well against experiments. We all then went ahead and looked for droplets which are not of spherical shape, and you can clearly see initially you start off with a very symmetric thing, but then very quickly in later stages you would actually see an azimuthal current which is going all through. Okay, so this is the first time anyone could see what is happening within the droplet, and this is just within the droplet. If you look at the vapor, it's quite complex how the vapor streams are. Okay, so you have this self-emergence of azimuthal currents, and this is the experiment we actually mimicked. So this is a weird shaped droplet. This is an IR camera. You can see that you've got this cold regions, and this cold region keeps oscillating here and there. And obviously this is like a vortex. There is a vortex here. Okay, so what we did is we took the final state of this droplet, which was this, and we mimicked it in DNS, and we could get somewhat similar patterns, at least in terms of temperature. So the plot I have made over there is the surface temperature, is the interfacial temperature. Okay. Now, yeah. So now what we can do is we can have, so this was basically one single droplet that we saw. Now what we can do is have multiple droplets. This is what Debruschi is currently doing at the moment. So when we have multiple droplets, we discussed yesterday that you have vapor shielding. So you can actually see, and what he has colored over here is the concentration in the vapor field. You can see vapor shielding happening close to that. So if you have 9 droplets, so actually he has gone up to 900, but we look at 9 droplets. If you look at 9 droplets, there's one guy which is completely in the center in comparison to others. So this guy, if you look at this very carefully, you will see that it's very symmetric. Okay, it's quite symmetric. The way your convection currents happen within the droplet, it's quite symmetric. But the corner droplets, you've got a lot of asymmetry going on. In fact, I'm going to show you another image where it looks like this. So you can say that that I think one of them is I should have probably indicated it properly. I think one of them is basically the center droplet. These are the side droplets. Okay, these are the side droplets, and this is what is happening within the droplet. Okay, so you can clearly see that there's a lot of activity going on within the droplets, and if you have a population of droplets, these activities, you can't just say, you can't just add a single droplet and get a population domain out of it. You really need to do these simulations. Okay. So what did DNS reveal? The DNS revealed that, especially if you have a non-spherical droplets, you have azimuthal currents that can kickstart and that can change your heat transfer patterns. If you have a deformed droplet, typically when you have a deformed droplet, it's not necessary that your contact angle is going to be the same all through. It will have a varied contact angle, even that is considered. Okay, and obviously if you have multiple droplets, you have vapor shielding. Okay, you have vapor shielding. So I think that's what is the take home message from here. Any questions before I start boiling? Sorry?
How much error it takes place if you simulate this case with RANs and DNS?
We will not use RANs here because there's no turbulence. We'll not use RANs at all because the Reynolds number here is, you've got a stationary droplet and your Reynolds number is completely based on capillary scale. So the Reynolds number is less than 1. So I would never go to RANs. Any further questions? Okay, so let's. This is something which Debryschi is doing. So he's now putting multi-component droplets. So we'll have a species equation in the liquid phase, and then you've got the modified surface tension force. So this is work that is ongoing at the moment. Now, now my question to you is, what's the difference between evaporation and boiling? What is the difference?
Evaporation is a surface movement from liquid surface to when it is converting into vapor. For boiling, I think that's a different also.
No, I mean, yeah, I mean, evaporation can happen at the contact line as well. So you have, it's a phase change process. Both of these are phase, but what is the main difference between the two?
Evaporation occurs at any temperature, but boiling occurs at
Yeah. What is the thermodynamic difference between the two? We talked about VLE there, vapor liquid equilibrium. So it's a slow phenomenon, it's an extremely, but boiling is a very fast phenomenon. It's a non-equilibrium thermodynamics. So essentially your phase change model is completely different in boiling. Okay, so when you have evaporation, you are at the mercy of vapor liquid equilibrium thermodynamics. Here you don't have that time at all. It's basically, in case of boiling, in fact, in case of boiling, it's a very fast phenomena. All it has to do is it has to take in heat from somewhere, change its phase, and conduct the heat the other way. Okay, so basically this is how it is. So an important aspect is obviously boiling is very important, whether it's nuclear reactors, whether it is even microfluidics, we use even cooling microelectronics, we use boiling as well. But the most important thing is boiling is dependent on wettability and surface pattern, and this is what we're going to see now. Okay, so here you will see the Kahn-Hilliard model in its full force, but here what we are doing is, if you see the phase change model, it just says that liquid takes in some heat, all that heat is taken into evaporation, and then there is a loss from vapor as well. So basically your phase change model has changed completely. It has nothing to do with equilibrium. Okay, in case of evaporation, if you had an interface, you had temperature you had different temperatures at different points. In case of boiling, this is a constant temperature. Okay, so you're not even worried about surface tension. So there is no such thing as Marangoni effects in boiling because the temperature is constant. If your water is boiling at 100 degrees Celsius, your interface is at 100 degrees Celsius. Water boils at 100 degrees Celsius to develop steam at 100 degrees Celsius. Okay, so all it is doing is change of state. So that's what we're doing here as well. So you've got very similar set of equations, except that the phase change model is different. The other thing is obviously we use the Kahn-Hilliard equation. It's identical to what we did in evaporation, except that this guy is quite different. So S is basically your phase change model there. Okay, now, and you got the set of, and one of the important things in boiling is gravity plays a huge role. Okay, gravity plays a huge role, so I cannot ignore gravity, and you can see that there is a bond number here. Okay, so bond number is the ratio between gravity and surface tension, so that is there. Okay, so if you look at this, and the other thing is, because we are looking at boiling, in evaporation, we started from a droplet seed. Here, we are going to start from bubble seed. So basically, you've got a vapor bubble, and basically that is going to, and this is, you can have, you can go from a hydrophilic surface to a hydrophobic surface. So when you have a hydrophobic surface, so this is hydrophilic surface. So in a hydrophilic surface, you've got more liquid penetrating into the vapor. So you've got theta less than 90 degrees. But if you have a hydrophobic substrate, your vapor spreads in that way. Okay. So you can actually have, it's a reverse of what you have in a droplet. But again, you start off with an initial condition. You will see that you'll see this evaporation patterns. You start off with this. I mean, there's no rocket science here. So basically, the initial conditions are very similar. You've got the temperature of the wall is the temperature imposed, usually the boiling point. You've got, again, or slightly more than, you can have a degree of superheat as well. The bulk temperature is at the saturation temperature, which is at boiling point, and then you kickstart the simulation. Okay. So the idea is that we want to look at how wettability improves it. So before we do complete wettability analysis, we're going to compare it with some experiments we did it in Edinburgh. So in experiments in Edinburgh, we are taking a silicon wafer. Okay, the surface is silicon wafer, so it's as smooth as possible, and we use FC72 as boiling on it. Okay, and here what we do is we compare the diameter. We look at the diameter of the bubble and we compare it with simulation data. So the blue is experiment and the X's are simulation. So not perfect, but we are on the ballpark. We are representative of what is there. And these are the parameters we are looking at. So this is for FC72 and whatever the hydrophobicity was, I don't remember. But this was the FC72 characteristics. Okay. The first thing we also do, we also define something called as population density. So if you look at normal industrial surfaces, you don't have one bubble there, you've got a million bubbles there. Okay. So the first thing we want to check is we want to define something called as initial population density. That is the number of etched points, number of nucleation sites with respect to the surface area, with respect to the available area. And based on that, we can actually calculate, we'll change the parameters of wetting and so on and so forth. Okay. So if you look at the physics of it, so when you have boiling, you will always find that as your vapor bubble departs from the surface, it leaves behind a residual film. And the extent of residual film determines the next nucleation event and all, and so on. Okay, so that's an important thing to look at. So what we do here is we look at, we consider a case where theta is 25 degrees, and basically we increase the number of bubbles. We can see that if you see the gray area, this is the residual film that is left behind. Okay, so what I'm showing you here is if you increase the number of bubbles for 25 degrees, the amount of film left behind hardly changes. So essentially you can say that the residual film, the volume of the residual film is a weak function of the number of bubbles in your domain. Okay, so no matter how many number of bubbles you have, the fraction of residual film left behind is nearly the same. So it doesn't change. However, if you change the wettability of the system, you will find that if you go for theta equal to 135 degrees or 120 degrees, you've got large amount of film which is left behind. Okay, but again, none of this changes with respect to the number of bubbles. So this is the number of bubbles. So you keep increasing. This hardly fluctuates much, but essentially the hydrophobicity or the hydrophilicity of the substrate determines the amount of film that is left behind. This is important because this regulates the heat transfer coefficient or the heat transfer resistance offered by the film. Okay, so basically, if you increase your contact angle in this case, the amount of residual vapor increases. I mean, this is also intuitive, obviously. So you increase your hydrophobicity, you'll have more amount of gas on your surface. Okay. Okay, so this is a very large simulation that we did. It's about 1.5 billion cells. So you can see that you've got huge number of bubbles which are starting. So, and this is, you can see that my student has put it in a regular array. It's a regular array and it's actually simulating that. And the reason we are doing it is we are developing scaling laws. So now if you look at this, so as your bubble evaporates, as your bubble departs, it pinches off, and each one has a slightly different departure time. In fact, we're going to show you how the convection currents come into picture here. Okay, so this is a very large simulation. So it's a pilot scale boilerplate. I think the number of etched nucleation sites is about 1,000 or something like that. So if you look at this carefully, you will see that there's a lot of activity going on between the bubbles. Okay, there's a lot of activity going on between the bubbles. In fact, if you have a single bubble, you will have convection in the liquid phase, but then that is almost like natural convection. If you increase the number of bubbles, and if they're placed close to each other, you actually go away from natural convection. Okay, and that's what this slope indicates. So if you increase the number of, this is ND is the number of bubbles. So if you increase the number of bubbles, this is the slope of the Froude number. The Froude number is basically the convective velocity in the convective velocity in the liquid phase here. Okay, so this is obtained directly from simulations. Okay, so you see that as you increase your number of bubbles, you have with respect to Froude. So if you plot Froude with respect to ND, the exponent is 0.9. It's approximately 1. For a single bubble, it's approximately 0.5. For a single bubble, it will be 0.5. That is a natural convection. But then, at some point, when you increase the number of bubbles, you have a rapid change. So this was somewhat close to free convection. This is a mixed convection. It's not yet forced convection. Okay, so there is actually a transition from the method of convection that is happening in the liquid phase that is there. Okay, so you can see that you can get a lot of information out from DNS. Again, as I mentioned, that simulation, which is the large simulation, would have taken about 24 hours. But the amount of time taken to get these results is immense. Okay, if you look at it carefully as well, you can also analyze the droplets which are, so what Jada did is she also looked at the spacing between this. So if you had a very packed edge surface, then what you can see is you can see deformation of the bubbles. And she also looked at the deformation and the effect of deformation and convective current. So the effect of deformation hardly has much of an effect, which we know, but it was basically an academic thing which she wanted to check. Okay. The other thing she checked is basically the stages of growth. If you look at the bubble growing, it goes into this necking stage. At some point, it has the maximum. This is a Nusselt number with respect to time. At some point, it reaches the maximum, and then somewhere here in this region, you got a departure. Okay. So what she's trying to plot, what she will plot now is this particular region of maximum Nusselt number. Okay, and she will plot with respect to Grashof. And so the reason we look at Grashof versus Reynolds number is that's how usually people do free convection. Okay, so if you look at that, we can, and if you go this way, you populate more bubbles. So you can see that there is a clear change in the coefficient here as well, exponent here. Okay. This is again the main plot. This is a plot where she has done several simulations. Each dot is one simulation, and here what she is plotting is the Nusselt peak, that is the range Nusselt peak, as a function of contact angle and as a function of population density. Okay, so you can clearly see that if you have a hydrophilic substrate, you've got the maximum heat transfer coefficient, and you can maximize the heat transfer coefficient further if you have more number of droplets, if you have more number of etching sites. So basically, the conclusion here is that if you have a hydrophilic substrate, it's great for having a high heat transfer coefficient. Okay, and the more number of sites, the better it is. She did it for random distribution as well. There's hardly any change in the result. Okay, so very quickly we can see that you can use DNS to actually resolve crucial engineering problems, especially, and if you have access to, you can exploit supercomputing facilities. Yesterday we were discussing about the supercomputing architecture in India. There's also this Airavat in CDAC, which is huge. Okay, so you can, if you get a chance, you can probably use it and exploit to go into pilot scale simulations, very large scale simulations. The purpose of CFD is to help engineers design better things. Okay, we have these design laws based on Reynolds number. You can have these scaling laws, etc. But CFD can give you more than that. CFD can tell you what is happening inside, provided you ask the right questions. Provided we ask the right question, that's the most important thing. Okay, so you can do boiling systems, you can do evaporation systems. You can also look at the hydrophilicity or the hydrophobicity of the substrates. You can, and then basically, one thing that we are doing at the moment is, obviously, no continuum method is good for nucleation, because nucleation is a molecular dynamic phenomena. Okay. However, we can use some other mesoscopic analysis. So this is not a CFD, this is not a DNS simulation, it's an LBM simulation. But LBM has to be also made sure that it is able to replicate real systems properly. So there is a lot of work which is going on to understand nucleation as well. We have done some nucleation using MD, but nucleation is in a molecular scale. So you cannot do large surfaces, you can only do very small surfaces. Okay. And the next step, what we are doing here, we have shown bubbles which are completely fixed to a contact line. We are also doing dynamic contact lines at the moment. So there's a student who's doing it. That's his first objective. So with this, I would like to thank you for the entire course. So you can see that droplets and phase change are extremely active areas. Okay. Phase change in particular is an active area. We are looking into various things. We are looking into solidification and melting as well. Okay. And why is it important? Because when people want to say that we want to minimize the energy requirement, we want to make sure everything is energy efficient, you need to understand phase change there. Okay. There's almost no system which does not use phase change. Okay. If you look at a distillation column, I'm a chemical engineer. If you look at a distillation column, the integral component of a distillation column is, I can draw a column for you. You've got a column which is probably the size of a 10-storied building, maybe. Okay. The feed goes here. This is where your petroleum feed or whatever feed goes here. Here you have a reboiler. Okay. So you've got a reboiler which actually feeds back the gas into the system. Okay. So the gas goes up, and then over here you have a condenser. Okay. And all the purified components go out of the condenser and the reboiler. Okay. And distillation is fundamental to any processing. You will not have your petrol, you will not have your clothes, you will not have any refined product without distillation or any of these methods. We will not have a modern society without it. Okay. And all of this is a function of phase change, whether it is forming gas or whether it is forming liquid there. Okay. So this is a fundamental problem for everyone. Okay. Even if you look at modern cars, many people are claiming great advantages of batteries, but battery fires, you can't stop them. You have to just abandon the vehicle and go. Okay. And basically battery, so you need to have, people are thinking more about cooling batteries. Okay. And that requires phase change. You can have a phase change material, molten salts, or probably something like a refrigerant as well. But refrigerant only happens at a small scale. So people are looking at molten salts, and other things. But that's a very difficult problem. So you look at any sort of a system, and people claim to have energy transition technologies or whatever it is, you need to have phase change there. So unless and until we rigorously understand it, we will not be able to design the system. Okay. So within my group, we look at a lot of these things. We look at boiling on slippery surfaces. We look at spray boiling. We look at clouds, because condensation and clouds are very interlinked. We look at, obviously, you've seen multi-component evaporation, salts, and things like that. We do that. The other thing I would like to mention is, you cannot have only one method to give you answers. You have to use a three-pronged or a multi-pronged approach to give you a complete picture. Okay. So one method, so people who rely just on DNS, people who rely just on modeling, people who rely just on experiments, they are unveiling only a small part of the curtain. There's a bigger show going on behind it. Okay, if you want to understand that, we need to see other methods. Okay, so with this, I would like to thank you. So I had so the first group of people until here, Damon, they're my PhD students. So most of the recent work I've shown so far is by them. Big thanks to Halim, Glenn, and Rodrigo. They have done, they shared some of their, so they are experts in capillarity. I'm not an expert in capillarity. Okay, so I actually use their methods, and these are all my collaborators over the years. And so you can see elements of all their work in my slides. Okay, I had a fantastic time here. Going from having Sidhu to going to this Markandeya temple and Parashar Lake and all that. So it was a brilliant thing. I loved it. Okay, so I can thank all of you for going through this journey with me, and it's great. Your place is great. So enjoy the most. I'm sure I'll be back at some point. I don't know when. Thank you. When is the next one? It's at 11 o'clock.